8,000 RPM. That's where top fuel dragsters explode off the starting line today, launching with such violence that drivers experience forces that would knock most people unconscious. But in 1985, launching at anything close to that number meant instant tire smoke, parts scattered across the track, and a wasted run. The clutch technology simply didn't exist to harness that kind of power, until an Ohio mechanic named Dale Armstrong decided the rules didn't say he couldn't reinvent the clutch entirely. Picture this. It's March 1985 at the Gator Nationals in Gainesville, Florida. Armstrong's driver, Kenny Bernstein, rolls into the staging beams in his Budweiser King-top fuel dragster. The competition watches, expecting the usual 6,500 RPM launch that everyone runs. The tree drops. Bernstein's engine screams to nearly 8,000 RPM, a sound that makes every crew chief in the pits snap their heads around. The car doesn't smoke the tires. It doesn't shake. It launches like it's been shot from a cannon, pulling a 60-foot time that shouldn't be possible. By the time Bernstein crosses the finish line at 272 miles per hour, every team in the pits is scrambling to figure out what just happened. This is the story of how Dale Armstrong outsmarted the entire NHRA establishment with a clutch design so revolutionary that it changed top fuel racing forever. A modification so simple, yet so effective, that when competitors finally discovered his secret 2 years later, they couldn't believe they hadn't thought of it first. To understand the genius of Armstrong's innovation, we need to understand what top fuel teams were dealing with in 1985. These weren't your father's hot rods. We're talking about 500 cubic inch aluminum engines running on nitromethane, a fuel so volatile it doesn't need a spark plug to ignite under pressure. These motors were producing somewhere between 3,000 and 4,000 horsepower, though nobody knew the exact number because dynos that could handle that power didn't exist yet. The sport had evolved from its roots in the 1960s when guys like Don Garlits were happy to break 200 miles per hour. By the mid-1980s, Top Fuel had become a technological arms race. Teams were running superchargers the size of beer kegs, cramming 65 pounds of boost into engines that rebuilt themselves between rounds. The NHRA rulebook was relatively thin on technical restrictions. As long as your car met basic safety requirements and displacement limits, innovation was encouraged. But everyone had the same problem. How do you transfer that immense power to the track without turning your rear tires into smoke? The standard approach was a single-disc clutch with a centrifugal management system. As engine RPM increased, weights would fly outward, progressively applying more clamping pressure to the clutch disc. Teams used different weight configurations, different spring pressures, different friction materials, but they all used a single disc of uniform material. The physics were brutal. At launch, you needed the clutch to slip enough to avoid overwhelming the tires, but engage quickly enough to accelerate the car. Too much slip, and you'd burn up the clutch before half track. Too little slip, and you'd smoke the tires instantly. The window for success was measured in hundredths of a second and pounds of spring pressure. Dale Armstrong wasn't your typical crew chief. Born in Saskatchewan, Canada in 1941, he'd grown up fixing farm equipment before moving to Ohio and opening a speed shop. He approached racing problems like an engineer, not a mechanic. While others relied on feel and experience, Armstrong kept detailed notes on every run, every weather condition, every component failure. He'd joined Kenny Bernstein's team in 1984, bringing a reputation for unconventional thinking. Armstrong spent the 1984 season studying clutch behavior with an intensity that bordered on obsession. He installed data recorders, primitive by today's standards but revolutionary for the time, that measured clutch slippage, drive shaft speed, and G-forces. What he discovered was that the single-disc clutch created an all-or-nothing engagement. The transition from slipping to locked happened too abruptly, creating a spike in power delivery that either broke traction or broke parts. Here's where it gets interesting. Armstrong's solution came from an unexpected source: automatic transmissions. In an automatic, multiple clutch plates engage progressively to smooth out gear changes. What if, Armstrong wondered, you could apply that same principle to a racing clutch? Not to change gears, but to create a progressive power application that the single disc couldn't achieve. The NHRA rulebook specified maximum clutch diameter and the number of discs you could run, up to 3. But it said nothing about what materials those discs had to be made from, or whether they all had to be the same. Armstrong saw his opening. Working in secret in his Ohio shop during the winter of 1984-85, Armstrong began experimenting with different friction materials. He sourced clutch lining materials from industrial suppliers, companies that made clutches for mining equipment and oil rigs. These weren't racing parts. They were designed for completely different applications, with different friction coefficients and heat tolerances. The configuration he settled on was brilliant in its simplicity. 3 discs total, as the rules allowed. But instead of 3 identical discs, Armstrong used 3 different materials with carefully selected friction properties. The first disc, closest to the flywheel, used a soft organic material with a low friction coefficient. It would engage first, but slip considerably. The second disc used a medium friction sintered bronze material. The third disc, furthest from the flywheel, used an aggressive metallic compound that would lock up solid once engaged. But the genius wasn't just in the materials. It was in how Armstrong tuned the centrifugal weights and springs to apply pressure at different rates to each disc. Using a combination of different weight sizes and spring rates, he created a system where the soft disc would engage at launch, allowing controlled slippage at high RPM. As the car accelerated and the centrifugal force increased, the medium disc would begin to engage, adding more clamping force. Finally, the hard disc would lock everything solid for the full power transfer down track. The first test came at Bernstein's shop in February 1985. Armstrong had told Bernstein he'd been working on something but hadn't revealed the details. When they fired up the car on the starting line, Armstrong told Bernstein to launch at 7,800 RPM, nearly 1,300 RPM higher than their normal procedure. Bernstein thought Armstrong had lost his mind. The first pass was revelatory. The car left the line harder than ever before, pulling a 0.94-second 60-foot time, 0.2 quicker than their best with the conventional clutch. The tires didn't shake. The motor didn't bog. It was as if the car had traction control decades before such systems existed. By the end of the test session, they'd made 5 runs without a single parts failure, unheard of when testing new combinations. Armstrong made his crew sign confidentiality agreements. He installed the clutch assembly himself, away from prying eyes. He even went so far as to paint all 3 discs the same color so that casual observation wouldn't reveal the different materials. When other teams asked about their improved performance, Armstrong credited everything except the clutch: new fuel mixtures, different gear ratios, weight distribution changes. The 1985 season was a masterclass in misdirection. At Phoenix, Bernstein won with a 5.42-second pass at 263 miles per hour, numbers that had the competition scratching their heads. The 60-foot times were consistently 0.2 quicker than anyone else could manage. In an era where races were won by thousandths of a second, 0.2 was a lifetime. Other crew chiefs tried to spy on Armstrong's operation. They'd casually walk by when the clutch was out, hoping to spot something different. Armstrong would deliberately leave conventional single-disc clutches lying around the pit area as decoys. When competitors asked direct questions, he'd give technically true but misleading answers. Yes, they were running 3 discs, just like the rules allowed. Yes, they were using centrifugal management, just like everyone else. The data from 1985 tells the story. Bernstein's Budweiser King dragster recorded 14 60-foot times under 0.95 seconds. The next best team managed just 3. In eliminations, Bernstein had a better reaction time and 60-foot time than his opponent in 82% of rounds, an unheard-of consistency rate. The car won 5 NHRA national events and set low elapsed time at 8 others. But here's the technical beauty of what Armstrong had created. The progressive engagement didn't just help at launch, it transformed the entire run. With a conventional clutch, drivers had to carefully modulate the throttle in the first 100 feet to avoid tire shake. Too aggressive, and the tires would break loose. Armstrong's system allowed drivers to go to full throttle immediately and stay there. The clutch became the traction control system. The heat management was equally impressive. A single disc trying to handle 4,000 horsepower would reach temperatures exceeding 200 degrees Fahrenheit. The disc would literally glow cherry red between rounds. Armstrong's multi-material system distributed the heat load across 3 different surfaces with different thermal properties. The soft, organic material acted as an insulator. The bronze disc dissipated heat through conduction, and the metallic disc could handle extreme temperatures without degrading. By mid-1985, the competition was getting desperate. Don Garlits, the sport's elder statesman, publicly accused Bernstein's team of running traction control, which was explicitly banned. NHRA technical inspectors tore the car apart after a win at Indy, looking for hidden electronics or mechanical aids. They found nothing illegal because there was nothing illegal to find. The clutch met every specification in the rulebook. The 1986 season saw Armstrong refine the system further. He discovered that by varying the thickness of each disc, he could fine-tune the engagement characteristics for different track conditions. A thicker, soft disc for hot, slippery tracks. A thinner one for cool, sticky conditions. He developed different friction material combinations for sea level versus altitude racing. The clutch became not just a power transmission device, but a tuning tool. The numbers from 1986 are staggering. Bernstein's car averaged 0.936 seconds to 60 feet for the entire season. The next closest competitor averaged 0.981 seconds. That might not sound like much, but in top fuel racing, that's the difference between winning rounds and watching from the trailer. The car recorded the first ever 270-mile-per-hour pass at the U.S. Nationals, a milestone that had seemed impossible just 2 years earlier. But Armstrong knew the secret couldn't last forever. Other teams had started experimenting with multiple disc configurations, though none had figured out the different friction materials trick. At the 1987 Winter Nationals, Armstrong noticed crew chief Austin Coyle examining a used clutch disc Armstrong had discarded. Coyle was running his finger across the friction surface, feeling the different textures that heat cycling had revealed. The moment of revelation came at the 1987 Spring Nationals in Columbus, Ohio, Armstrong's home track. Ed McCulloch's crew chief had figured it out. Not the exact materials Armstrong used, but the concept. McCulloch's car showed up with a multi-material clutch setup and promptly ran a 0.93 60-foot time in qualifying. The secret was out. Within 6 months, every competitive top fuel team was running some variation of a multi-material progressive clutch. The aftermarket responded quickly. Clutch manufacturers like L&J and Boninfante began producing multi-disc sets with different friction materials specifically for drag racing. What had been Armstrong's secret weapon became industry standard. But here's where Armstrong's genius truly showed. While everyone else was copying his basic concept, he'd already moved on to the next innovation. He'd discovered that by using different diameter discs, smaller soft discs and larger hard discs, he could create an even more progressive engagement. The NHRA rulebook specified maximum diameter, but said nothing about minimum. Once again, Armstrong had found a loophole. The physics behind this were elegant. A smaller diameter disc has less surface area and therefore less total friction capability. But it also has less rotating mass and responds quicker to application pressure. By using graduated diameters, Armstrong created a clutch that engaged in stages not just through friction differential, but through mechanical advantage. The smaller disc would engage first with minimal rotating inertia. As speed built, the larger discs would engage with their greater friction surface area. This second-generation progressive clutch pushed Bernstein's performances even further. In 1987, the car recorded the first sub-5:30 second elapsed time, running 5.289 seconds at Dallas. The 60-foot times dropped into the 0.92 second range consistently. The car won the NHRA championship, Armstrong's first as a crew chief. The impact on the sport was transformational. Within 2 years, every top fuel car was launching at RPMs that would have been unthinkable in 1984. The progressive clutch allowed tuners to use more aggressive supercharger overdrive ratios, knowing they could control the power delivery at launch. Engine builders began designing components specifically to work with high RPM launches, including stronger connecting rods and redesigned oil systems. The safety implications were significant too. Before Armstrong's innovation, clutch explosions were common and dangerous. The single-disc clutches would literally explode from centrifugal force when they exceeded their design limits. The multi-disc system distributed the centrifugal loads, reducing catastrophic failures. The NHRA noted a 40% reduction in clutch-related DNFs in the 2 years after progressive clutches became standard. Armstrong's innovation also changed the economics of top fuel racing. A single-disc clutch that could survive 1, maybe 2 runs cost around $2,000 in 1985. Armstrong's multi-disc setup cost about $30,500 but could last 6 to 8 runs with rebuilds. Teams were spending less on clutches overall while going faster and more consistently. It was one of those rare innovations that improved performance while reducing costs. The data recorders Armstrong pioneered became essential tools. Teams could now see exactly how each disc was engaging throughout the run, allowing for precise tuning. The clutch became the most data-logged component on the car, with sensors measuring temperature, slippage, and pressure at multiple points. What had been a mechanical component became a computer-controlled system, though the basic multi-material concept remained unchanged. By 1990, top fuel cars were running elapsed times in the 4.90-second range, a full half-second quicker than the best times from 1985. While engine development and aerodynamics contributed, every crew chief credited the progressive clutch as the enabling technology. Without Armstrong's innovation, the massive horsepower increases of the late 1980s would have been unusable. The modern top fuel clutch is a direct descendant of Armstrong's 1985 design. Today's versions use up to 6 discs with computer-controlled pneumatic pressure management instead of centrifugal weights. The friction materials are space-age ceramics and carbon fiber compounds. But the fundamental concept, multiple discs with different friction characteristics engaging progressively, remains unchanged. Every 11,000 horsepower top fuel dragster launching at 8,500 RPM owes its ability to do so to an Ohio mechanic who saw a loophole in the rulebook. Armstrong went on to become the most successful crew chief in NHRA history, winning 16 championships with various drivers. He was inducted into the Motorsports Hall of Fame in 2008, but he always said his proudest achievement was the progressive clutch, not for the races it won, but for how it advanced the entire sport. In interviews, he'd note that his innovation made top fuel racing both faster and safer, a rare combination in motorsports. The story of Dale Armstrong's secret clutch is more than just a tale of racing innovation. It's a reminder that sometimes the biggest breakthroughs come not from inventing something entirely new, but from applying existing technology in ways nobody else has imagined. Armstrong didn't invent the multi-disc clutch or different friction materials. He just saw a connection nobody else did and had the courage to pursue it in secret until he'd perfected it. Think about that for a moment. In an era before computer simulations and advanced modeling, one man with a notebook and a willingness to experiment changed an entire sport. He found speed not in the engine or the aerodynamics, but in the few inches of space between the engine and transmission. He proved that in racing, as in life, sometimes the most important innovations are the ones nobody sees coming. Today's top fuel cars run the quarter mile in under 3.7 seconds at over 330 miles per hour. They accelerate from 0 to 100 miles per hour in less than 0.8 seconds, pulling 5.5 Gs that would cause most people to black out. None of this would be possible without the ability to launch at maximum RPM and progressively apply that tremendous power to the track. Every time you see a top fuel car leave the line, you're watching Dale Armstrong's legacy in action. What's your favorite example of racing innovation that changed the sport? Let me know in the comments below. And if you enjoyed this deep dive into drag racing technology, hit that subscribe button for more stories of the brilliant minds who pushed motorsports beyond what anyone thought possible. Until next time, keep those engines screaming.